Alright, from AP, now we are going to move into geometric progressions. We are going to move into the second form of progressions that we have, which is geometric progressions. So just as in case of an AP, we had a common difference of D. In case of a GP, GP is basically a series wherein the Tn by Tn minus 1 or Tn minus 1 by Tn, this is going to be a constant. So the successive terms, if they are divided, you will always get a constant. And this constant, just as in case of AP, it is known as common difference. In case of a GP, it is known as the common ratio. So we have a common ratio out here. So if we look at the sequence of a GP, this will look something like this. A would be the first term, the second term would be AR, the third term will be AR square, the fourth term will be AR cube, and so on and so forth. So if we just look into this, we can very well imagine that if it is the nth term, then the nth term will be given as AR n minus 1. This A happens to be the first term of the GP, and R is known as the common ratio. How do we get this common ratio? If we divide the successive terms, for example, if we divide A square by AR, which are both successive terms, we will get R. Again, if we happen to divide AR by A, we will get R. So between two successive terms, the common ratio is always going to be R. This R can either be a negative number, this R can be a positive number, this R can be a decimal, and this R can be a fraction as well. So R has its own criteria. So this forms a GP. In a GP, we constantly multiply the number by a increasing amount of the common ratio, R, R square, R cube, and so on and so forth. Now, how do we calculate the nth term of a GP? The formula for the nth term of a GP is A R n minus 1 upon R minus 1. This is in case the R, that is common ratio, is greater than 1. If it is greater than 1, then we have A R n minus 1 R minus 1, and in case R is less than 1, then we have A 1 minus R to the power of n 1 minus R. So these are the three things that you have to remember. In case of a GP, the Tnth term is A R n minus 1, and the sum of n terms is A R n minus 1 upon R minus 1 in case R is greater than 1, and in case R is less than 1, this will be A 1 minus R n 1 minus R. How do we find the sum of infinite terms of a GP? This will be A 1 minus R. So this is always in case R is less than 1. We cannot find the sum of infinite terms of a GP, in case the common ratio is greater than 1. We can only find this if the common ratio is less than 1. So sum of infinite terms of a GP will be A upon 1 minus R, where A is the first term and R is the common ratio. So these are certain formulas that we have to just keep in mind while doing problems in a GP. Now we'll very quickly refer to some of the features of a GP which we have to remember or use when we get problems in GP. So the first thing that we have here is, if each term of a GP is multiplied or divided by a fixed non-zero constant, then the resulting sequence is also a GP. For example, if we have A, the other one is AR, then we have AR square, and so on and so forth. If we get this multiplied by a common term, which is going to get this multiplied, let's say by P. So what will this become? AP, then we have APR, then we have APR square, and so on and so forth, which will mean that again, if this is a GP, how do we prove that this is a GP? We will get the division of Tn by Tn minus 1. This has to be a constant for a GP. Now, if we get this divided, so we have APR out here, which gets divided by AP, you will get the answer R. If you divide APR square by APR, again you will get the answer as R. So this forms a GP. Again, if we happen to divide this, so let's say we have a series of GP A R square, this entire thing, if we divide by a constant, let's say p, so we will have all of them as a by p, a r square by p, and so on and so forth. Now if we happen to divide again tn by tn minus 1, the second term in a succession by the previous term, so we have here ar by p divided by a by p, obviously these two get cancelled and we have r. Again if we divide ar square by p by ar by p, these are going to get cancelled and again we will get the common ratio as r. So this again happens to be a GP. This again happens to be a GP. So if every term of a geometric progression is multiplied by the same number, the resulting sequence is going to be a GP. If every term of a geometric progression is going to be divided by the same number, the resulting term is going to be a geometric progression. Now if A1, A2, A3 and B1, B2, B3 are two geometric progressions, then the sequence A1, A2, B2 and A3, B3, this is also an GP. So let's say we have a sequence A1, A2, A3, this is basically a GP and so we can say that A1, let's say this is A1, this will be A1R, this will be A1R square and so on and so forth. This is the other way of writing it. And again we have B1, B2, B3. This also happens to be a geometric progression. Let's say the first term here is B1. We can write this as B1 R dash. Let's say B1 R dash square and so on and so forth. If we happen to combine them in the sense that we get them multiplied. So A1 B1, A1 B1, which means basically this is A2 and this is B2. So we have here A2, B2, then we have here A3, B3. This is also a geometric progression. How? Let's look into this. A1, B1, what will we have in A1 and B1? This is just going to remain as A1, B1. If we look into A2, B2, what is going to give you? A1R in place of A2, and B2 we have B1R. So this is going to give you A1, B1, R square, R dash, I'm sorry. A1, B1, then we have A1, B1, R dash, then we have A3 and B3. So A3, in place of A3 we can write A1 R square, and in place of B3 we can write B1 R dash square. So this is going to give you A1, B1, R square, R dash square. Now let's look at these successive terms and see if they actually form a GP. So here we have, if we happen to divide this one by this one, A1, B1, R dash by A1, B1, we are going to get the common ratio as R dash. Let's say if this is the same for this one. So if we divide A1, B1, R square, R dash square upon A1, B1, R dash, this is going to get cancelled once and you will be left with R dash. So this is the common ratio for both of them. Hence, this entire thing A2, B2, this also is a GP. So if there are two GPs and if we happen to combine the terms by multiplying them, multiplying the corresponding terms, so this one will be A1 into B1, A2 into B2, A3 into B3, then the resulting sequence will also be a GP. Why? Because it is giving you the same common ratio, R dash and R dash. Okay, now we'll move, just as we have in case of AP, arithmetic progression, we have something as arithmetic mean. And arithmetic mean between two numbers A and B is given by A plus B by 2. In the same way, for a geometric progression, if we have two numbers A and B and we have to insert a geometric mean between them, this looks something like this. So let's say if we have another number set, let's say G, and this is the geometric mean. So it means that if I get this divided by G, then G by B, because the common ratio for this will be equal to the common ratio for this. So I have divided this by this. We can go the other way around as well. If we, let's say, divide this by this, then this will be equal to B divided by G. In any case, we are going to get the same ratio. So either we divide this by this, or the second by the first. In the same sequence we get this. In this case we'll get G square is equal to AB. In this case also we are going to get G square is equal to AB. So which means G is equal to under root AB. So in case we have to insert a geometric mean between two numbers which are A and B, then this will be A GB, and the value of G is given as A to B. So this is how we are going to get the geometric mean of two numbers. So this we can say that A, G and B are in GP. So if three numbers are in GP, we can very well say that the middle number is going to be the product of square root of the extreme numbers. So in this case, we say that A, G and B. So in this case, G is equal to AB. We have two products. So this is basically equal to 1 by 2. In the same way, if we have A and B, and if in between we have A1, A2, A3 and so on till n terms. So here we have n terms. So this will become, if we have to calculate the geometric mean between these two, the geometric mean will be given by A1, A2 into A3 and so on and so forth till an to the power of 1 by n. Just as we have in this case A and B to the power of 1 by 2, in the same way if we have n terms between them, this will be 1 by n. So if A1, A2, A3 are in GP, so let's say if A1, A2, A3, this entire sequence is in geometric progression, then we can say log of A1, log of A2 and log of A3 and so on and so forth, this will be an AP. Let's look into it. So let's say A1 is equal to A, and in this case A2 is equal to AR, in this case A3 is equal to AR square and so on and so forth. So if we say log A1 will be equal to just equal to log A. Then we have log A2. This is going to be log A plus log R. Do we see this? A multiplication means a plus in log. Then log A3, this is going to be log A plus log R square, which means log A plus 2 log R. Similarly, we can say log A4 will be equal to log A plus 3 log R. So if you closely notice here, log A1 is equal to log A, log A2 is equal to log A plus log R, log A3 is equal to log A plus 2 log R, and log A4 is equal to log plus 3 log R. If you see this is constantly increasing. So in this case we can write log AN is equal to log A plus n minus 1 into log R, and this is nothing but an AP. So in this case this will be an AP. So if we have a geometric progression which is A1, A2, A3, then we can conveniently say that log A1, log A2 and log A3 are in arithmetic progression, and the vice versa also holds true, which means that if log A1, log A2 and log A3 are in AP, then we can say that A1, A2, A3 are in GP. So if we are given any series which is a log series, we can conveniently say that A1, A2 and A3 will be in GP.